For sure, we're all excited for the panel discussion. But before that, let's enjoy first learning from the distinguished lecture to be given by of course, our distinguished speaker. So
Thank you very
uh,
much.
I believe all the participants are now coming in. And so again, welcome back, participants. And welcome to our last distinguished lecture of this 2 day summit. Please remember to stay with us until the last segment. The last panel discussion is not to be missed, happening right after this session. So, to talk about the integrated STEM for all, urgent post pandemic educational needs and opportunities for change, we have with us a professor at the Center for Advanced Research, Institute of Education, University of Chile. He has a doctorate degree in electrical engineering from UCLA and has received the Best Paper Award at the 10th International Conference in Methodologies and Intelligent Systems for Technology Enhanced Learning, MIS Fortel 2020 in Italy last October. Let us welcome Dr. Roberto Araya. Dr. Araya, the floor is yours.
Well, good evening, everyone. First, thank you for inviting me to this very interesting and important conference. STEM integration, I think, is the future and the future now. And I'm from Chile. Here is really 8:48 a.m. So this morning, the world is round. So now I'm going to share my presentation. Share. Okay. Okay, so integrated STEM for all. We believe that integrated STEM is for all students starting from kindergarten, elementary school, high school, and of course, college. And post-pandemic has pushed us to technology and also certain needs and certain opportunities for change. So why integrated STEM? Consider the following. Everybody has a smartphone for navigation, going to some places, for example, going from my home to a meeting, driving. You could also maybe have another system that is recommending something different, but it's not navigation. Maybe it's another things, and maybe another system in their cell phone, and another system recommending something. For example, it's recommending to you doing some surgery. So you have four systems recommending what to do in a possible surgery, or even a fifth system surgery, and they are talking together and maybe suggesting to you what to do. But not only suggesting to you what to do, but also they could be doing in your life systems that are making decision for you, and systems that are talking within each other, and somehow all of us need to know what is going on. What are the limitations? What are the biases? How this is working? And this is very important now, from now on, in the life of every citizen. And this integrates not only computational ideas, technology, engineering, but several sciences like geography, like physics, and biology in the case of surgery. So it's really it's really integration. And now we have this pandemic. So what are the needs first, and what are the opportunities? The needs are, first, we have seen that almost all the students have gone on studying at home, at distance, doing some work. And for example, we were pushed to have the students work at home, and then somehow send the information of what they're doing to their teachers. And for example, we have to develop some app to help the teacher assess and be in contact with them. Now, there is this very important problem yet, particularly in poor countries, in poor areas, for example, in our country, in other countries, is that most of them, they don't have good internet connection. Most of the household that don't have a good, they don't have computers, but almost all of them have smartphones. smartphone, but with not always with a good connection. Sometimes, the connection a couple of times a day when they go to a mall, then they have Wi-Fi or they go some places, so it's not continuous. So that's the basic need. And here is an app that also kids can use to do math and science and STEM. This is just a screenshot of the smartphone having a math and science problem. And what is interesting, we've been pushed to have this application even if you don't have internet. So when you go someplace, you have Wi-Fi, internet, download all the activities, and then the student can work at home with no internet. And when their parents go to some place, they have some Wi-Fi, then this will upload and the teacher will receive. That's what the teacher receive. At the left is a map of the country, part of the country. The darker regions mean in those regions there's more heavy use of this application. In the second screen, there is a zoom, and you see all these dots. White dots are schools, and the small smartphones are schools using the system at that day, at that moment. And this blue the blue component in the let me see, can you see? Yeah. Oh, sorry. One or two. Yeah. So these blue ones means the school have worked a lot, all the students from the school. But when it's red means there is some videos that the teacher or some of the parents have uploaded to the system. So everyone in this community can see ideas from other teachers or other parents. And here the right is the the curriculum. So how much has been doing from writing, reading, and each of the learning objectives. So in this way, the pandemic has pushed us to introduce technology in this very specific condition where most of the families, they don't have very stable internet connection, but they have smartphones. What other technologies we've been using in this moment is speech recognition. This here is the teacher talking, and while she talks, in this again using just the smartphone, so it talks in a live class. It could be online or offline. At the end, the telephone will tell her what's the proportion of time that she was lecturing. For example, was 45% of time. How much of the time was waiting? Yeah. So all this give aids to the teacher what to doing. Here's the time from 0 to 1 hour, the moment she was lecturing, the moment the administration, the moment she was asking open-ended questions, this moment which she was waiting, the moment which she presented experiments could be online experiment. So you see the power of smartphones now for teachers. So what we are learning is the importance of smartphones for students and teachers. And at the end, it will summarize the whole class, saying this graph, concept graph, with was the most important. She talked was about energy and related with more energy, yeah, more energy. And for this, here you have contamination, concentration. These are they are the main words, concept that the teacher taught, and CO2, yeah, but related with energy and contamination. And what was the link between the concept that she in her lecture? Here is a summarize of different lectures of electricity, and these means are more close. So it is able to summarize all the lectures and see what is the relation between them. For example, radioactivity, these are farther away from the electricity. So here's another picture of science skills with math skills, content and math skills, content with science skills. And each one of these is a lesson. So you can see a summarization of lesson, compare one lesson to other different lessons of this teacher. And here you see, this is just one lesson. Again, this graph is science skills, math skills, content, math skills, content, science skills. So this is the trajectory of a lesson. That's another way of representing the lesson. So what we see again, the importance of smartphone. Smartphone, for, in this case, for teacher to help and to help him or her do her lessons and see the trajectory of her lesson and how much integrated is this in this case math and science kids and with content. But it's not only speech. Telephone also do some image processing. Here is let me see. Oh, cannot see. Supposed to be a movie. But what is this? This is a movie with the skeleton. They are moving, but and now I don't. Let me see. And this was exactly what's behind. So this was really a classroom, and you can see the motion of all the teachers and all the students, and so automatically we produce this skeleton, and from there we could get the attention of the kids, what they were doing, and the kind of non-verbal activities that the teacher was doing, like going around, looking at the kids, not only with eye gaze, but also with the position of her body. So, and this we have been doing also this a teacher now online, and so every moment we could see what was his, how he was talking to the kids doing an online class, and all of them is it gives us a very important non-verbal information about for the teacher, so how he or she is doing. So we have with smartphone application for the kids with not very good internet, but using smartphone application for the teachers to summarize what she was talking about, all the concept, and a summarization of also of her movements and how this non-verbal behavior with the kids. Okay, so we have seen what have been the needs. Let's see now the opportunities. So basically, needs means okay. Pandemic has pushed us into technology, and particularly to internet, but considering very weak internet in most of the population that and using smartphones because that's what their parents have, smartphones. Opportunities. We see that every day we see all kind of graphs in the media. Here is all this year, and this is a confirmed new cases in COVID and different countries. So one good thing about this is that all of us are starting to get used to analyzing graph trends and trying to understand why is this producing and the effect of different strategies. So I think it's a good opportunity now to reflect on this problem. I belong to this Asian Pacific group inside project that where is Dr. Hichan Lee is, Dr. Wayari is from Indonesia, Dr. Hichan Lee from Korea, Dr. Masami Soda from Japan, and all the Asian Pacific. And we see here a big opportunity because it's a big problem. We don't need to motivate students about this problem. This problem, is so important for us that we need to understand what's going on. So it's a big opportunity. So I'm going to show some activities we've been working in this APEC, Asian Pacific group, using the problem of the pandemic. We have done that before, for example, for forest fires. 1 year completely about forest fires, very important in several countries. So it's a real problem. The kids watch on the TV, that problem, they feel it, just outside their home or sometimes in their home. Other times we have seen, floods, in Philippines, very important. So how, this is a really big problem. How can we use STEM, integrating all kind of concept from science and math and engineering in order to understand and finding solutions. Other issues we have been using, where we're working just a whole year in tsunamis and so on. But now it's COVID, so coronavirus. So modeling the pandemics to understand what's going on. So some ideas we've been working. So first model, okay. So this is for just kindergarten or first grade. So you have here several people. These are represent model as these circles. The red one is the one that is contaminated, infected. So the very simple model is once if you touch someone, a very close touch that is infected, then you will be infected next day or next 4 days. So what will be the next picture? This will be the next picture, yeah? So now we have two. And what will be the next picture? Well, next picture is exactly the same because the other ones are further away. So you see here a very basic model of propagation phenomena. It's science, in physics, and, and in biology, all these propagation phenomena is very important. For example, tsunamis is basically propagation phenomena. For example, forest fires also propagation, the fire. That is a very basic model, and kids could just do some coloring here, understand the rules of this model. So this is the first model. Okay, here is another model. Oh, sorry, it's the same model. Now we have this configuration. So what will be the next? Here is the one that is infected. So in the next time step, you will see now these two, because these two are here. Next time you will see that this one will get contaminated, infected, okay. Next time you will see this one, because it's touching this one. So here you have, next time you will see this one, and you see that these other ones, they will not be infected according to this model. And okay, and next time, well, next time you will see that this is the same. So somehow we would say this converge because these other ones are isolated. So this shows somehow the importance of isolation, to be isolated in order not to be infected. So we have been working this with kindergarten students, first grade students, understanding this model. And they like it. It's fun to do all this coloring. And they could discuss that maybe you don't need to touch somebody to be infected. So this is more than a person, would be the person in the center, and this was just one, it could be 2 meters from the person. So this would be the circle is more than a person. It's a circle, 2 meters, in radius around the person. So you are close than 2 meters, maybe you could be infected. You could discuss also that it's not automatic you will get infected. So it's certain probability, maybe 1 in 10 times you will get infected. So you see how discussing with their kids, they start modeling and integrating some math idea about patterns, some biological ideas about infections, and so you start integrating to produce a model, a mathematical model, but with a graphic representation of this phenomena. And this is a problem that they have to handle every day. And you see the importance of these 2 meters of distance, social distance. Okay, so the second model that you could consider is a bit more sophisticated. So people move around. So here you have, this is just a billiard table. You have here 3 people in this area. Here you have more people, and here you have more people. Maybe, and you see that since they move around, they're not static. If they move and they touch, then they will get infected, let's say with probability 1 or 1 in 10. And so the first question is, everybody is moving. It's moving around. So the first question is, where is going to be more collisions between people and their infections? And you could do this experimentally. A small, table. This is just a table for kids. Doing at homes, very inexpensive, maybe $10. And you could see, and counting, you can put your phone with the camera and register the video, and then count the number of collisions. Interestingly, this problem is exactly the problem in particle physics, when you have collisions and you turn it off of statistical mechanics. But here, every ball is a person, and they start moving around, and you can see how many collisions you have. So that depends on the amount of population in this area. So that depends on the density. So if you are in a countryside far away from the other, even if you move, there's not going to be much collisions and not much infections. But in a city, very crowded city, for example, let's say the subway in the metro, with very close to each other, with motion, you will have a lot of collisions. So somehow the infection depends on the density. So the idea of density, number of people in a certain area, like in this table. But You also could see that you could have posts of different sizes. What does this mean? This means this person, if he's using a mask, she contaminates very little. They have to be very close to her. Here in this extreme case, that's persons are not wearing a mask. Then you see in this case that if you are at, if they touch and it's very big radius, they will contaminate. So this is the case using a mask. This is the case not using a mask. When you're using a mask, you have to be very close to the other, like in the dentist, really, very close, maybe less than half a meter to maybe get infected. But if you're not using a mask, it's much easier to get infected. So this is a way of modeling, a population with mask without mask. So that's important of mask. We have seen two parameters: density of population, and then using or using mask. Does make a big difference in the number of collisions, thinking in a physics way, a number of infected people think it in a epidemiological way. But also, it's important in the motion. For example, let's say this is static, but let's say in 1 second, on 1 minute, this is the trajectory of this person. So he moved all of this. But this is the same person, but moving more slowly, so less mobility. So you see that if you have less mobility, the possibility of collision is less than here when you have more motion. So the more you move, more mobility of the population, more possibility of collision. For example, here we have two persons with a high mobility. Maybe they could collide at some point with this one. And here you have more persons with high mobility. Possibility of collisions are higher. So somehow you see the probability of collision has to do with this area, the wide area of these trajectories. So this is estimation of probability of collision. If the proportion of this wide area of over all the green area. So students can do this using their smartphone and recording a video and seeing the collision, but you can have an estimate using these papers that we put here that show the trajectory of the people and seeing the possibility of collision, probability of collisions. So this is a person without mask moving. So this is the whole trajectory and a possibility of colliding with this one. So here is all the possibilities. You see that the mobility of population is very important as well. It's not only the density. Here is more people than here, but it's but I know are they moving the same? But here is less people, and here is just less density, but moving the same as here. So it depends on three factors. So you have now a model saying that the infection depends on the density of population, depends on they're wearing a mask or not, and depending on the mobility, so how fast you are moving. If you are quiet at home, just staying at home, then you are more in this situation, you don't move much just to this local supermarket. But if you go to work and a lot of people like in the subway moving all around, then possibility of collisions is much more. Collisions in the terms of physics, in the terms of biology, means infected people because they touch each other, probability of being infected. So we see that we have gone from the very basic model for kindergarten and first and second grade. There was no motion. Now to a more sophisticated model, you could do experiments. You can see this way, understand. You are somehow taking ideas from physics, from collision. You have ideas from mass, like density, area, density of population, physics of velocity, motion, and also ideas from um, from biology and epidemiology. So they're integrating all these ideas in order to understand the world and why we have to stay home, not move so much, why we should use masks, and try to avoid crowded places. Okay, so that one was about the velocity. A third model. Now go to a third model. So we see here the pandemic and opportunity to understand the world. And it was interesting that we don't need to motivate students about this problem because this problem they are suffering every day, for a whole year, maybe this year also, at least half a year, they will have this problem. So it's a very meaningful, important problem for all of them. So here we have a problem. Here is the population, typical. There are 15 people, and after 14 days, it's 14, one of them will die. These are infected people. So the strip left, 15 block represent 15 PCR positive persons, PCR positive, and 14 days later, one of these persons dies. So this is just a physical model of what really is happening. This is a simplification because some people die at 10 days after being positive, some have 20 days, be positive, sometimes even more than months. But not all of them die. From 15, for example, in some countries like here, for 15 positive PCR, this test for coronavirus, one dies. That's roughly the statistics, and you have the representation. But now you have this problem. These are the PCR positive. So how many people are really infected? You said yes, it's really the positive. So how can we know, estimate all the infected? Because not all the infected will go and do the PCR test. That depends very much on the country. But so that's a really interesting problem. So, and it's very critical. We would like to know in every country what are the numbers of people really infected. So how can we handle this problem? And so one idea is to see what happened doing proportional thinking, what happened with the Diamond Princess. Diamond Princess, they have around, let's say, 1,000 passengers, and all of them got infected, but only some of them died. So we know that roughly from 150 people infected, one died. And so using this, and then I post to using this information, how can we solve this problem? So we know that in general, from 150 people, one died. But so you know from here to there, but also you know from here to this, because from 50 people positive, one die. So now you see there is a 10 factor between this and that. Now this is a rough estimate. Every country is a bit different, but using this information, like in this uh, cruiser that it was in Japan, and you have all people counted, all of them infected, then now you can estimate with something very important. How many people in my country or in my city is really infected? It's a very practical and important problem. Now let's go to another model, fourth model, machine learning. Machine learning, everybody's talking about machine learning. Maybe it's the most important idea in computer science in the last decades. Machine learning really has been around maybe for 50 years, but now in the last years, so important, let's say, for speech recognition, for image processing and recognition objects, for autonomous vehicles, for also for medical applications. So, so here is a problem for first graders. So in A is what is called training set. All these are people, different people. This is old lady, is a young guy, and here is a boy, here is a girl. Okay, so this is a sample of people, and some of them are infected. You see, they have this pink um, mark, infected. This is not infected, not infected, not infected, and this is really infected, and this old man infected, old lady infected. This is a young guy not infected. Okay, so the idea is, can you see a pattern there? Could be infected or there are people that could die. Let's say infected and died, this red one. Now you looking at this, you have to try to understand a pattern, and then you have a new set of people, and you have to predict who of these people will be infected and die. So this is what is called the training set. This is a basic idea in machine learning. You train the computer with information, in this case of part of the population, and you know who has been infected and who has died or not, and you know their age, their gender, and other information. And then you have this testing set, means once you think you were able to obtain a pattern, then you you have to try to guess here what you learn from here, the pattern you try to guess here, and then you can compare. If you how was your accuracy. So this is a very basic idea in machine learning. You have a training set where you train the computer. In this case, you find patterns, and then your testing set where you predict, and but what was who in this case were infected and died. But then later on, you show it to the machine and see what was your accuracy to it, how good you were able to predict. So this is a basic model, very interesting for and simple for kindergarten, elementary school kids. Now let's go to a more deep model, machine learning. So we use information from the medical virology a journal. This was published in March, so 2020, and was the first publication information with some patients. Here are the patients. They had information from 17 Chinese patients, and they have the gender. This is the case 1 to case 17. These are the first 17 deaths in China, in Wuhan. They have the gender, male, male, male. This is a female. The age of each one of these patients. For example, this was a female, 48 years old. First symptom, fever. Comorbidity, yes, she had. Surgery, not available information. And first symptom to death, 41 days. And this one is male, case number 4, 89 years old, no fever, first symptom. Comorbidity, yes, he had. And surgery, yes, he had a surgery. And he died just 6 days before, after first symptoms. So let's try to apply here machine learning ideas to find a pattern. Who will die because who will die very soon and who will have will die later on. So it's just from this first 17 days trying to see a pattern there, the difference between in which kind of patients population will die very quick and not so quick. So that it will be very practical problem, because if we solve this, find this pattern, we can tell the physicians if is this really urgent or not. So the priority, because this person probably will die in 6 days, 10 days, or in 40 days, so you have more time. Okay, so how will we do this? How will we solve this? This is a really practical problem, applying machine learning, some statistical math ideas to a very concrete biological, epidemiological problem in medicine. Well, in this case, we will try to distinguish very severe, not so severe. That's what we're doing. We're not doing here death versus no death. We need other kind of data for that. So will die, will not die. All in this our case, all will die. But some will die very soon, and other ones will take it. You have a little more time. So, and this data is public, it's real, it's published. Everybody can access that. And we started using this at the end of March, because it was published at the beginning of March, and the student would see, okay, here we have the data. Can you make some prediction? You're going to tell the physician what to do. So now here we have this number line with the age, people from 40 years old, 80, 90 years old. We represent the information this way. And circles are people that died in more, I think, than 10 days, something like that. And so it was the medium of the number of days after symptom where people die. And these crosses are people that die very soon, less than the medium. So you see a pattern already here in this number line. You have 1, 2, 3, 4, and you count, you get 17 cases. Most of the circles are at the left, like around less than 70 or 69. And most of the crosses are the other way. It's not perfect, but you see this pattern. So you from the presentation, using just number line, you can do it doing this even in elementary school, represent information, and you will see the pattern. So we see here clearly that people less with age less than 69 years old, they will, survive longer than people that are 70 years old or older. There are some exceptions, of course, but that's the pattern. So now you will see statistical ideas here applying to this medical and very important problem. So somehow here kids could try to decide if this would be a good threshold or not, and discuss if you put the threshold there or if you put it in another place, number of errors you would produce if you put it in another place. It turns out that this is a big discussion. So where to put this threshold to take the physician look? Less than 69 and more than 69 is a critical age you have to consider, or maybe you could see more than 85 here, but then you have all these cases, too many errors in the circles. And now if you put it too much there, okay, you are perfect in the circles, but also a lot of errors with the circles, at the right there. So this is a big statistical problem, very interesting and crucial in machine learning, where you put this threshold in order to have better accuracy. Finally, from there, you could produce what is called summarize in a decision tree. First system to death, 16 days was the median. You have 8 cases with first system to death more than 16 days. And you have 9 cases with first system to death less than 16 days. And the critical factor was age. Was not comorbidity, was not surgery, the other values that we had before, but age was the most important. With less than 69 years old, then you have more people that live longer. More than 69 years old, you have a lot of people that live less, 7 cases that live out of these 10 cases here. So you see that we get this statistical idea. This is basically machine learning, graphic representation to produce and be able to produce a pattern. A pattern is very important and very practical because it means what to do in hospital, what should physician do, what they to pay attention to. And here, according to the real data published in March 2020 with the first 17 cases, you could see this doing just with middle school math and just representing in the number line, even elementary school math, you could get the pattern, and you get able to produce very practical recommendations to hospitals and physicians, saying, okay, watch 69 years old and older is getting more complicated, and you need to prioritize this kind of patient because you have less time. So we have seen ideas from teaching and learning post-pandemic. Teaching means you have to do at distance, but most of the kids, they don't have computers, they don't have internet, but using the smartphone and using, like we develop applications that are almost offline, means only when you go to some place you have Wi-Fi, you would upload the exercise, the activities, and to your computer download, and then also upload to the servers and the system where you it already have been doing. You can access the information of your school, what are doing other teachers, other parents and other schools, and get ideas from them, so build this community. And we also giving tools to teachers because they, somehow, since they're using the computer to talk and do some activities, you can summarize the main concept they are using, and they can compare with other teachers and see if they're the central idea in their lecturing and when they're teaching is the same as other ones. And also seeing even the non-verbal language, how they're moving, they're making eye contact with whom, and even the position of the body. Because it's not only important the gaze, but it's also important the body. You can be having a gaze with somebody, but your body is pointing to another place. It turns out that body position is almost, or sometimes most important, just a gaze. So the position somehow send you a signal that you are paying attention to this other, for example, to the student. So we saw this with the technology. We can use the smartphone. That's what we learn, the importance of smartphone. Everybody has smartphone, but with very weak internet connection, unstable and not continuous. But with your smartphone, you can see what's happening in your region, what is happening in all the schools, what other people are doing, what some ideas. We ask here teachers, some parents to do things at home. You click in the school and you see videos they have produced, 1 2 minutes videos with some idea how to teach something. And it's really interesting. We have some publications if you're interested. The kind of ideas they produce, like using concrete materials, something very innovative. Sometimes some teachers have very interesting ideas. Sometimes some parents. So some games. So to how to play at home with some games that teach the basic ideas, and also, for example, using, for example, like Muppets to talk. You talk to a puppet, and when you talk to a puppet, somehow this helps to metacognition. So how did they have been using this? The teacher, the student is teaching her puppet, her teddy bear, how to do something. So it's really interesting how this helps to the metacognition, because when you are in the teaching mode, sometimes it's known you learn more. It's called the protege effect, protege from protect. So somehow, if you teach a peer, a classmate, or your teacher teddy bear, and then it's interesting for reflection and metacognition, and that helps really to understand better. And with technology, you also would get a summarization. Every parents and teacher could see summarization of all the curriculum, the strands, and and if for each strand, also all the learning objectives, if they've been reached or not reached. So we have seen in the broad picture with integrated STEM for all, from kindergarten to high school and college. I haven't put examples here in college. I was thinking more in primary school, middle, and high school. We have seen that we have really some needs in this situation, and it somehow is solved with smartphones, using smartphones basically, and without and considering that you probably most of your students don't have a stable and continuous internet connection, but still you can go around with semi-offline applications. And we see that also, since we have pushed technology, teachers now can have immediately a summarization of the lecturing. For example, in this case, this is an application we've been developing with some people and researchers from Finland, University of Jyväskylä, and we've been working already more than 6 years on what's called Smart Speech Teacher Talk, and then her smartphone then summarize the main concept of her lecture. And also this non-verbal communication is so important, and that also that with the skeleton will produce how is your what you're doing, how you're moving, your gaze, all this information. And then the pandemic is terrible, but give us a strong motivation to everybody to understand and see the effect of different policies, like using masks, like social distance, like mobility, and also using machine learning. We can recommend some idea, find patterns to recommend to physicians and hospitals how to prioritize, the attention of patients. So you will see here's a big opportunity to do modeling. Modeling is the glue between different parts of science and math and technology, and then to engineering to produce solution. So thank you very much. My name is Roberto Araya. Here is my email if you want to send to send an email. I can send you publications. We'll be working with in the APEC group, Asian Pacific group, using these models, and also the application for the teacher. We've been working heavy with this with the Finnish researcher from University of Jyväskylä in helping the teacher. So thank you very much. I'll stop sharing.
Thank you, Dr. Roberto Araya. Just reading the comments from the participant discussions, we all love the models you showed us. It's very simple, it's clear, it tackles current contexts, for example, COVID, and it's easy to understand and do. We also loved what you shared about resources and ideas using just smartphones, especially since smartphones are ubiquitous. Some may not have laptops, but most would have smartphones. So thank you for
Yeah.
sharing these very wonderful ideas and resources.
Thank you, Dr. Araya. What I love of the presentation is the emphasis Sabs on the use of models. I think models can be really essential tools to foster an integrated STEM and authentic STEM education and basically STEM literacy.
Right. And
Thank
that's all
you.
the time we have left for this session. Unfortunately, we can't
Oh,
take in any questions anymore, but we'd love your presentation, Dr. Raya, and thank you for spending time with us. It's noon there, it's nighttime here. We really appreciate you and your ideas. So thank you so
well,
much.
thank you very much to you and all the audience. I think the most important message with me here is that COVID is terrible. There's no doubt about that because so many people died, so many people. But at the same time, it's a big opportunity to STEM because it's the opportunity to understand what's going on, to produce solution, and to integrate different fields. So you STEM has helped us to solve maybe one of the biggest problems. The biggest problem initially is motivation. What we are going to do, so it's something meaningful or not. And what more meaningful than trying to help with some solutions to control the pandemic. Thank you very much.
And those are wonderful closing statements. Thank you so much, Dr. Araya.
Once again, let's click the thumbs up button to say thanks to our distinguished speaker, our deep appreciation to our guest speaker or distinguished speaker, Dr. Roberto Araya. So we'll now move to our last panel discussion. Please click the up next button, which will appear on your screen, or go back to the stage. Choose the panel discussion, which is our next session in this 2 day summit. Just and of course, click join. Once again, thank you so much, Dr. Araya. We hope to see you in person soon.
Thank you.